Alright, here we are again. Let's get going. I have a couple examples to work through, and then we can be done. Alright, so let's move along here and learn how to use the method of joints. Alright, simmer down, let's get started. Okay, so let us look at this here. Using the method of joints, determine the force in each member of the truss shown. Determine whether each member is in tension or compression. Now, I'm going to use a variety of methods for this. First of all, I am going to use the, I am going to draw the reactions on here. I'm going to have Cy, Cx, and dy. Again, we'll have joint C will have reactions in the x and the y direction because it is a pin joint, while joint D will have a reaction in only the vertical direction because it is a roller joint. Now, just looking at this, I see. Do y'all notice something peculiar or particular about this truss? Something that might be useful? It's symmetrical, yes. It is perfectly symmetrical, which means if our dimensions are all symmetrical, if our members are all symmetrical, and all our loadings are symmetrical, then we can use arguments based on symmetry. So that only works if we can only use arguments of symmetry if both the geometry of the truss and the loadings on the truss are symmetric. But as long as everything is split 100% right down the middle, everything has to be symmetric. What do I mean by that? Well, I mean that the force in this member has to be equal to the force in this member. The force in this member has to be the same as this one. The force in this one has to be the same as this one. This is a symmetric system. It is a mirror image. So therefore, corresponding members must have equal forces. So I'm going to solve for the reactions. First, the external reactions. Get external reactions. Get external reactions. So I'm going to say, well, first of all, I have a very simple one. There are no horizontal forces on this truss. So clearly, Cx is 0. I have no horizontal loading applied, therefore the Cx has to be 0. If there was horizontal loading on it, and we can have horizontal loading on it, the reaction here would not be 0, the X reaction. But these loadings here are purely in the vertical direction. Therefore, we will not have any horizontal reaction. Now, I could do a balance of moments or something, but you know what? I am going to use arguments of symmetry. I like doing that. That's kind of cool. It's rare that I'm able to do this, so I'm going to take advantage of it while I can. Sum of forces in the y direction are going to be equal to Cy plus dy minus 300 times 2 minus 600 equals 0. However, Cy is equal to dy. They are one and the same. Cy has to be equal to dy. This is a symmetric system. Therefore, I now have 2Cy. I could say that 2Cy is essentially equal to, this is negative 600, negative 1200, so 1200. From this, I can get that Cy equals dy equals 600 pounds. We now have all of our reactions, just like that. All right. Now, we need to start. I'm going to draw an exploded free body diagram. You know what? I think I'm going to. This is going to take up a lot of space. This is going to not be the most space efficient thing, but I think I'm going to duplicate this. Okay. Questions so far?
Did you get the 2CY?
Again, I just said, I basically, the question was how to get the 2CY. I essentially replaced dy with cy, 2CY. Algebra. They are equal. Okay. All right, I'm going to copy this. Duplicate slide. I'm going to call this slide 11.5. And I'm going to delete this here. This won't be very space efficient, but whatever. All right, so we now have our reactions. We know that cy and dy are both 600 pounds. £600 and 600 pounds. All right, now I'm going to draw an exploded free body diagram. Observe carefully. I'm going to draw all the joints. And this is one area where drawing on a screen versus drawing on the board is at a bit of a disadvantage, because the one advantage of the board is I do have more room to draw.
Is CE one piece or is that three pieces?
C.
E. No, BE.
BE is 3 members. They'll have 3 different forces. The question was, is BE 1 member or 3 members? It's 3 members with 3 different forces. Every time you have a joint, you'll have new forces. Yes?
Since it's symmetrical, can we just draw half of it?
We could, but I'd rather draw the whole thing in this case just to illustrate it. The question was, since it's symmetric, could we just draw half of it? I said, no, let's draw the whole thing in this case, just because it's the first example with trusses, and I do want to draw the entire thing. D and E. I need to put that a little further out, I think. And E. And now I'm going to draw all of the forces on here. Now, as I do this, I am going to, anytime a force is at a diagonal, I'm going to show the force triangle. So first I'll have my 3, that looks bad. I'm going to have my 300-pound force. £300 force. And a 600-pound force. And a 600-pound force. Now, notice how I'm going to, actually, first let me draw the reactions on here. This will be 600 pounds, 600 pounds, and 600 pounds. Now, look at how I'm going to draw this, and how I'm going to label this. I'm going to call this FBC. And FBC. And all this means is the force that is in member BC. And look, initially I am drawing this in tension. So the question is, why are forces coming away from joints? Why is that tension? Well, if you consider a member like this and joints here, if I have a tension force on this member like this, in turn, the joints will be pulled like this. So this is a tension system. So I show all of the forces as tension initially, which means forces coming away from joints. And just for convenience, you could call them whatever you wish, but I usually just label them F subscript, where it's the joint number of the lower number or the lower letter, and then the upper letter. I keep it fairly simple. This is going to be FBC, this is going to be FCD, FDE, FAE, etc. Then I'm going to have FAB and FAE. Oh, I want to keep that space clear. FAE, or sorry, AB, FAB. And the force triangle for this one is going to be, let's see, this is 6 and 12. So in other words, 1 and 2. 12, 6, 1, and 2. Or root 5. That applies to FAB here. I believe so. Yeah, 1 and 2. Or sorry, 1 and 2. Because the overall horizontal length of member AB is 12 feet. The height is 6 feet. So that is a 1 to 2 ratio, and we get root 5 for the hypotenuse. So we have a force triangle, which we'll use in lieu of doing sine, cosine, tangent, etc. Okay. Then, let's see. I'm going to have FAC, FAC, and FAC. And the force triangle here, let's see, 8, 6. To me, this looks like a 3, 4, 5 triangle. 3, 4, 5, right? Like that, FAC. Then I'm going to have FAD. FAD. This one's just a flash in the pan. It's not going to stick around very long. Get it? It's never mind. Okay, that's really bad. Okay, and this one is also going to be a 3, 4, 5 triangle. Then, going through my own drawing, this one's just going to be FAB. And ideally, oh, sorry, this one's FAE, sorry. Ideally, you would have more space to write this and make it a little neater on paper or whatnot. FAE. And this is also at a 1 to root 5 triangle. Then we'll just have down below here the bottom chord, FCD, FCD, FDE, and FDE. And this is all the forces in this truss. This is a simple one. Please consult your various deities now. But thankfully, we do have arguments based on symmetry, so you can make this thing only, we're going to solve for only 1, 2, 3, 4. Now, so I'm going to do equilibrium on this joint by joint. So observe. Let us look at joint B. This is one type of thing that I really wish I would work out on a whiteboard, but that's okay. Or I just need to get like a gigantic computer with a huge screen or something, right? Okay. All right, so let's look at this. Let's do, I'm going to draw joint B. This is B. And again, the force is on here. Now, you don't need to redraw it every single time, but I'm just doing so for clarity. FBC and FAB. And FAB. And so I'm actually only going to need to draw 2 joints to solve this entire thing. If you believe me. Do you believe me? Okay. Do you have faith in me? Okay. I will not let you down. 300 pounds. Okay. Anyway. So now I'm going to just start by doing the nice thing about this is it is a pain in the butt to set up all these free body diagrams, but once you have them, you don't have to do a lot of really complicated sum of moments and picking things. The nice thing about the method of joints is, I mean, yes, it's a lot of work, but the nice thing about it, it's kind of like a zero thought method. So it's long, but it doesn't really require a lot of thinking. It's just kind of go through the steps. It's like digging a hole. It's the concept is not that complicated. It's a lot of work, but it's really not that complicated a concept unless you're digging like a 30-foot deep hole or a trench or this is not construction project management. I won't discuss trench building technique and safety technique. Anyway, that's another thing entirely. Yeah, major in civil engineering. I can teach you things like trench safety. Isn't that lovely? Anyway, so sum of forces I'm gonna do in the y direction first, because if I did x direction first, I would have 2 unknowns and I'd be sad. So I'm just gonna have negative 300 pounds, plus FAB times 1 over root 5. Now, my algebra teacher, Mr. Link, would tell me that I should not have a root in the denominator, but Mr. Link is not here right now, so we're going to ignore that. You're not the boss of me, Mr. Link. Okay, FAB is going to be then simply 300 root 5, correct? I believe. Come on here. 300 root 5. Is that, if I have mathed correctly? 300 root 5, which will come to, let's see here, 300 times root 5, and I am getting, let's see, something's not right. 670? Okay. 600, and that sounds about right. 670.8. 670.8 pounds. Then I can simply say, all right, look at this. On the same system, sum of forces in the x direction. And if I really wanted to, I could say, like, I could call that, you know what, I think I will. I'm going to say sum of forces b in the y and sum of forces b in the x, but that's kind of optional. Sum of forces about joint B in the x direction is going to be equal to FAB times, let's see, 4 over root 5 plus FBC. Huh?
I don't see them. Where the four? Isn't it 2 over root 5?
Oh, sorry, 2 over root 5. Yes, 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 sorry. Two over root 5. That was always 2. I have no idea what you're talking about. Times 2 over root 5 plus FBC equals 0. However, let's see. I know that FAB is 300 root 5, so that just becomes 300 times 2 plus FBC equals 0. Wait a minute, something's FAB here. I guess, yeah. That'll work. I guess what's bothering me is that just looking at this, it's really bothering me because I'm getting that this member here is in tension and this one's here is in compression, which in general is exactly the opposite of what you'd expect. Top chords are usually in compression and bottom chords are usually in tension, but that's usually with loads up here and your supports on your outsides of your truss, not internal supports like this. So the usual rules don't necessarily apply. But anyway, FBC, therefore, is going to be equal to negative 300 pounds. Oh, sorry, negative 600 pounds, yes. Negative 600 pounds. Yes, compression. This is compression. Yeah, and this one is tension. So this one, you know what, I'm just going to go ahead and label some of these. I'm going to say this is 600 compression. And by symmetry, this is also 600 compression. This one here is 670.8 tension. This is what I'm doing on this side over here is just symmetry. 670.8 tension. Oh, I probably should have. 670.8 in tension, like so. Now I need to draw joint C. And that will allow me to get the other 4 forces. C So by drawing the forces on, let's draw the forces on joint C here. So I'm going to have, let's see, 600 pounds here. I'm going to have, let's see, FBC is, I'm going to show it as, I'll just draw it as this, as the original drawing had. 600 pounds here. Actually, you know what, maybe I will just draw it how I know it really is. I know it's really in compression, so I'm just going to go ahead and really draw it in compression. It's going into the joint. 600 pounds here. I have FCD here, and I have FAC here. And my dimensions are, this is a 3, 4, 5 triangle. Let's see, 3, 4, 5.
How do you have 600 pounds coming from the left?
That is the question is, how do I have 600 pounds coming from the left? That is FBC here.
Okay, so you want to solve one and then go to the next joint? And
Exactly.
Solve one and then go to the next
Exactly. The method of joints is a step by step by step by step. We walk along the ladder, we pull ourselves up step by step, joint by joint by joint by joint. Yes.
First step is the place with the least unknown.
Generally, yes. The first step will be the place with the least unknowns. So if I had a really complicated joint with like 6 different members going into it, I probably wouldn't want to start there. In fact, I'm going to try to avoid that altogether if I can. All right.
And when on break, I noticed the ceiling trusses over that atrium out there are 6 joints.
Mm.
So you already got me thinking.
Those are space trusses. They're a bit more complicated. Yes.
Could you
Could I have used joint A? Yes, I could have.
Okay.
That would have worked just as well. Now, at first, it looks like, oh, I have three unknown. Well, no, I only have two unknowns there. But one reason I didn't do that is because I'd like the joint that has. Basically, I have this one I need to solve for and this one. And by doing just one joint, I can do both of them.
Okay.
Now, let's see. I'm going to do a sum of forces on joint C in the y direction. This will give me 600 pounds, this one, plus FAC times 3 over 5 equals 0. Why does it equal 0? Because it's statics class.
Oh, yeah.
But yes, static equilibrium as well, yes. FAC is going to then be equal to negative 600 times, let's see, 5 over 3, which 600 over 3 is 200. 200 times 5 is 1,000. So negative 1,000 pounds or compression. That's FAC. So we have 1,000 pounds compression here. Then finally, I'm going to just do a sum of forces in the y direction on joint C. And I will have, X, yeah, X, Y. What's a direction among friends? I mean, they're all orthogonal, right? And you know what? For consistency, sum of forces joint C in the X direction. There we go. So I'm going to have 600 plus FCD plus FAC times 4 over 5 equals 0. And so then this is, let's see, this is 600 plus FCD minus 1,000 times 4 over 5. So this is negative 800. This is negative 1. This is negative 800, positive 600, and those combine to FCD minus 200 equals 0. FCD equals positive 200 or tension. So FCD. Yes. No, wait a minute. Did I screw that up? What did I screw up? Something's not right. I really screwed that up. My labels here. FAC, sorry. Oh. I think I see my problem. I just labeled this wrong. AC is 1,000 compression. This is 1,000 compression. Did I label this one right? Yes. Okay, we're good. We're good. We're good. Yeah. And then this is 200 in tension. And there are all the forces inside that truss. All right. Questions on that? Yes?
So when expressing your answer on the homework or a test, you should express it as 200 parentheses T indicate.
I would say on an exam or something like that, yeah, you should probably, especially if asked, state whether it's compression or tension. The best way to do it is honestly I don't have quite room up here, but the best way to do it is probably just to create a little table and to actually just write out, these are the members, these are the forces within. In fact, on your exam, I might even give you a little table to fill out or something like that.
Okay.
All right, other questions? Fun, huh? Joy. Okay. Man, determine the force in each member of the gambrel roof truss here. I do not know if we have time for that, so maybe I'll just walk you through the general method instead. So we're not here till 5 o'clock. Well, no, it doesn't take that long, but again, let me just walk you through the method for this instead. What I'm going to do here is I would start by solving for the reactions here and here. Is this symmetric? Yes, this is symmetric. And here. I would start by solving for the reactions. Then I would go and break it down. It's basically the exact same as the other one. However, I am aided a little bit by what? Oh, yes, I'm aided by symmetry and also zero force members, both. This one is 0, and this one is 0. In fact, this actually might not take as long as you might think.
How do you tell that?
Oh, because the question is, why can I just tell it like this? And the answer is because I'm a wizard. Anyway, no, sorry. The answer is you have, math, obviously math. Anyway, collinear members. Collinear members. This pops out to me. I just see this. I see two members here. AC and CE are straight members. Just one continues right into the other. And this one, like that, is goes into this joint, and there's nothing to resist the force of this at this joint. Notice, it does not matter what it's doing on this end. If it is a zero force member on either end, the entire member is a zero force member. So I don't care what it's doing up here.
Simply 4 triangles now?
Sort of. Yeah, it's kind of just 4 triangles now. Yeah. So maybe it's not actually too bad. In fact, you know what? Let me try to see how quickly I can solve through this. Maybe I won't draw the complete exploited view. Maybe I'll just draw like little sub ones. Okay. Oh, yes, you're right. I got that backwards. Thank you. Derp. I'm used to the roller being over there, so yes. Although in this case it's completely irrelevant, so that's okay. So I'm just going to say this one is 0. Okay. Don't start packing up yet. We got a lot more work to do. Anyway, let's see. So this is symmetric, so we do get to use arguments based on symmetry again. So the total load on here now is 1,800 plus another 600, 2,400. So each reaction must be 1,200 pounds in the vertical direction. 1,200 pounds. Actually, this will not take that long because it's a nice. I see a lot of nice dimensions on this.
You want to do it?
Yeah, I'm going to do it.
Okay.
1,200 pounds. 1,200 pounds. So we'll be able to use. Okay. Anyway, back to seriousness. Okay. Okay. I'm quickly going off the rails here. So what is this? Oh, this is a highlighter. Okay. Okay. So let me draw a free body diagram just of joint A. So I'm not going to draw a big free body diagram for this one. If you really want to be proper, you could, but that's okay. I'm just going to do it piece by piece, work my way across. You don't really need to draw the whole one, I guess, if you don't want to, but either way is fine. So this is joint A. Kind of short on time, so I'm going to try to get through this. 1,200 pounds. And then I'm going to have 300 pounds. FAB and FAC. However,
Didn't you say you can go right through it, make it into a... You said you can cancel out those zero force members.
yeah, I'm not having that. I'm not having that there.
Oh, okay.
Oh, but yeah, I mean, it's going to be the same force in this one and this one. Anyway, so my force triangle. Hey, look at this. 6, 8. We got a 3, 4, 5 triangle. 3, 4, 5. So I'm going to do the sum of forces in the y direction first on joint A. Sum of forces on joint A in the y direction. This is going to be FAB times 3 over 5. Let's see, and then these will come to a total of 900 pounds upward, plus 900 pounds equals 0. And so FAB is going to be equal to, okay, that's 900 over here, 900 over 3 is 300 times 5 is 1,500. So negative 1,500 pounds or compression. So this is 1,500 compression. This is 1,500 compression. We've solved two. We have two members solved. Sum of forces about joint A in the x direction. I am going to have FAB times 4 over 5 plus FAC equals 0. And FAC is going to be equal to negative 0.8. I won't do that yet, actually. Negative 4/5 FAB, which 4/5, okay, so negative 4/5 of, so it's going to be a positive number. And then 4/5 of 1,500, let's see, that's 300, 1,200. 1,200 pounds. 1,200 pounds. Tension. Now check this out. So we have that. That's good. That's good. But now, 1,200 pounds. Tension. 1,200 tension. 1,200 tension. But this is a zero force member, which means this one has to be 1,200.
Oh.
And this one also has to be 1,200. So we are quickly seeing the behavior here. What is happening here is that this truss is acting like a large beam. The top chord, a string of members is called a chord in a truss. The top chord is in compression, and the bottom chord is in tension. That's typical of truss behavior under positive bending. We'll learn what positive bending is later, but generally positive bending is a beam that bends in this kind of shape. This is positive bending, while negative bending is a beam that's bending in that kind of shape. Huh? What? These zero ones? Oh, okay, why is this 1,200? Well, if this is 0, then this one is the only thing that can balance this one. So they have to be equal and opposite. They have to both be in tension. They have to be the same. Okay, let's look here now. What else can we do? Well, we could look at, let's look at joint B. I think, I'm trying to look at this and see which would be the simplest way. Yeah, let's do B. We don't actually have a lot of options here. So joint B. Let me draw joint B. B Okay, so I'm going to have FAB going into it. Notice I'm drawing it as going into the joint because it's compression. I know it's compression because I already solved that. FAB equals 1500 with a force triangle of 3, 4, 5. Let's see, 3, 4, and 5. I'm gonna just, you know what, I'm just gonna ignore this one, BC, because we already know it's 0. I have a 600-pound force here. 1,500 pounds here. I'm going to have a, let's see, FBE. I'm going to assume it's tension starting off. FBE and FBE is also a 3, 4, 5 triangle. And finally, I have FBD. FBD, and its triangle is not so pretty. Let me just draw this one out here. There's a little more room. This one is going to be, let's see, the height of this, the width of this is still 8. This is 2.33, and the hypotenuse, let's see, the square root of 8 squared plus 2.333 squared is 8.333. That sound right? No, something's not right. No, yeah, no, that's good. That's good. That's good. 8.333. 8.333, like so. Huh? Huh?
I don't see where you got that last triangle.
Oh, this triangle, the question was, where did I get this last triangle? This is FBD. I'm just looking at the dimensions. 8 feet on the width, 2.333 feet on the height. Huh? 2 feet 4 inches, yeah, which is a third of a foot. Okay, so now, oh man, this is going to get really ugly. Oh man, is there a better way to do this? Let me think about this. There is no good way to do this, is there? Oh well, I'm trying to avoid ugly equations, but there is no way in this problem, unfortunately. Sum of forces in the x direction is going to be, let's see, that is going to be 8 over 8.333 FBD plus 1,500, let's say BX, plus 1,500 times 3 over 5, this one here, plus FBE times 3 over 5 equals 0. All right, so then we'll have, let's see.
Maybe we could change that 2 feet 4 inches into fraction.
I'll just leave it as decimal for now, I think. It's good.
The first one should be 4 over 5 instead of 3 over 5?
4 over 5, let's see. Oh, wait a minute, that might be right there. Let me see about this. 4 over 5.
8 across and 6 up.
Oh, this one should, that's the problem. This is 4 over 3 as well, isn't it? Yeah. So they should both be 4 or 5, shouldn't they? Sorry about that. Those both should be 4 over 5.
Good guess.
4 over 5 and 4 over 5. Now, let's see. So 8 over, let's see here, times 8. I'm going to have 0.960 FBD plus 0.8 FBE equals, that's going to be negative 1200. And that's one equation that we'll need to solve. Negative 1200. Sum of forces B, or sum of forces about joint B in the y direction, we'll have negative 600 plus 1500 times 3 over 5 plus FBD times 2.33 over 8.33 minus FBE times 3 over 5. All that equals 0. And that comes to, let's see, so that's going to be, oh, that comes to 900, 300, right? 300, let's see, 2.3333 over 8.3333. So 2.0. Let's see, plus 0.280 FBD minus 0.8, 0.6, sorry, 0.6 FBE. We have simultaneous equations. Isn't that lovely? Okay, do you want me to solve it all the way through, or you think you got it at this point? Think you got it? Okay, let me show you what you would do. Let me walk you through the rest of this. We have these two equations. You would use a matrix, or you would use algebraic techniques. If I had a little more time and a better calculator, I'd solve this out more. Basically, you'd plug one into the other, solve for FBE, get FBD. That'll give you this one and this one. Then you'll just use a free body diagram about, say, joint D to get this joint here, to get this force here. All right, questions on that? And that's a general method for handling that. Let's see. And we could do this, but it's the same idea, except this one we won't be able to use symmetry. We're just going to have to keep going through it again and again and again and again. But there you have it. So that is the method of joints, and we will look at the method of sections tomorrow. So any questions on that? All right, I know this can be tedious. Stick with it. Give it a try. You should have some homework problems. Look at those. We'll be here again tomorrow, bright and early. It's 11-ish, 11:30-ish. If you have any questions, I'll be in my office later. Feel free to drop by. You have your homework problems. Just a sec. And let's see. If you have any questions, feel free to come up at the end. And I'll see you tomorrow. And as always, thank you.